After reading the definition of relations and functions and one and onto functions, now finally we read the definition of a group, because this lecture series is a group theory lectures. So what is group? Let G be a non-empty set and star is a binary operation on G. Then G is closed under star. What is star? Star is binary operation. And here now you have to study about binary operations. First of all, you understand binary operation with the help of the sentence. The binary operation is a mapping from a set to itself. For example, if you have a set, okay, if you have a set and you have a Cartesian product of this set, okay, then the Cartesian a mapping from a set to itself mean the domain and ranges are equal, or in other words, the set is closed. Binary operation is the set is closed under addition. For example, if you have a one set, okay, then you have apply some mapping or some function onto this set, and you achieve or gain one answer, and this answer belong to the domain category of the set, then it is called the binary operation. Okay, so binary operation, G basically group, basically we study about groups from the definition of a set. So group is a set, but the particular type of set which satisfy the following conditions. Our first condition is associative property hold under that operation. This binary operation can be addition, can be multiplication, can be union, or any other operation, but necessarily it is a binary operation. And for binary operation, you have to understand binary operation is such type of operation which is closed under that operation, means the answer of the after applying the answer of that after applying the operation, the answer our answer remains in our domain set from where we take elements for applying the operation. Okay, so associative property hold in the set. If associative property hold in a set G, identity element exists, and this is E star X and is equal to X star E for all X belongs to G, then inverse of each element exists. First property is associative property. So associative property means first you can apply a binary operation on first two elements, then third, or first last two elements, then first, then our results remain unchanged and left hand side answer is equal to right hand side. So this is associative property. Then we apply identity element, and identity element exists. Identity, what is identity element? Okay, for the better understanding of groups, you have to learn 3 or 4 basic definitions which are very helpful in our definition of a group. Then we definitely understand about groups. So I want to share my views or concepts about these definitions. Our first definition is binary operation. Second definition is identity element. Third definition is inverse of the group and inverse of an element. So what you know about binary operation. So binary operation, you know, is a such type of operation. Operation means plus, it can be a plus, it can be a multiply, it can be union, any operation. And operation, but the result of that operation also remains in our domain set, and it is a binary operation. After binary operation, we learn about identity element and inverse element. Identity element is that element which when we apply or operate on with some other element of the set, and our answer remain unchanged. For example, I want to clear this concept with the help of one example. For example, we have a set 0, 1 and 2. Okay, or we want to we have a set 0, 1, 2, and now I want to see the example of identity element with the help of this set name A. Okay, so this is the set, and here our binary operation, as I clear, binary operation can be addition, multiplication, or any other predefined operation, but here I use addition. So in binary operation, if we let addition, and this is our set, and we take identity is such type of element in that set A. When we apply this element to another element, operate this identity element to all other elements, our result remains unchanged. For example, if you add 0 plus 1, your answer is 1. Then if you add 0 plus 2, your answer is 2. So by adding adding is our binary operation. So by adding 0, or in other words, you say after applying binary operation of 0 with all other elements of set A, our results remain unchanged. So that's that is the definition. Then so from this we understand 0 is our identity element, because when you apply identity element, when you operate identity element with all other elements of set A, where A is for all A belongs to A, here for all A belongs to A, all other elements of A belongs to A, then this is our identity element. So hopefully we you understand better about identity element. So identity element is the element of the set, and identity element also belongs to the set G. First of all, when we do not satisfy all the properties of a group, our G is a set. We take a set G, and now we see the properties, following properties. Either this set satisfies all these properties, the set which satisfy all these 4 properties, then this set become a group. So first of all, we see associative property. If a set hold associative property, then we move forward to identity element property. We see either identity element is exist in this group, in this set, or not. So identity element, now we see identity element is already see identity element is that element which we operate and all other elements of set, and our results remain unchanged. And in addition, you know, our identity element is 0, and if we multiply, if we take binary operation is equal to multiply. If we take binary operation is equal to multiply, then 1 is our identity element, because if we multiply 1 by 2, then it is equal to 2, 1 by 3, then it's equal to 3. So our results remain unchanged. That's from this example we have clear idea about identity element, because identity element can be vary from one set to another set. For example, if we had one set A and it maybe it have 0 identity element according to binary operation which is applied on that set, and maybe some other set and it has one identity element according to the binary operation applied on that set. So binary operation can be varied from set to set or operation to operation identity element. Now we see inverse element. Inverse element depends on identity element, because when we apply one element and with other element, operate one element with other element, our results become identity. Then this element is our inverse. When we apply the element A, operate element A with such type of element, or this such type of element also belong to our set, and when we operate 2 elements and our result is identity, then here we say A is the inverse of this and this is the inverse of this. Okay, now for example, you multiply, or for example, you add 1 plus 0 is equal to 0. Here you see 0 is our 1. So here you see 0 is our identity element. So now you want to gain or attain identity. So you have to 1 minus 1. Here minus 1 is the inverse of 1, because we can write at 1 plus minus 1 and is equal to 1. 0. So here 1 plus minus 1 is equal to 0. So here 1 is the inverse of minus 1 and minus 1 is the inverse of 1. So from this we clearly understand what is inverse. So inverse of each element exists. Such type of set in which associative property hold, in which identity element exists, in which inverse of each element exists, and last but not least, abelian group. Abelian group mean commutative property also hold. Commutative property mean if you apply binary operation on two elements of a set and change its position, then our results become unchanged. Then it is commutative and abelian group. So, or called abelian group. So, first of all, you need to clarify these three properties. These are the main. Either it is a set is associative, identity, inverse, then commutative and abelian group. If commutative Lahore, then G is called commutative and abelian group. Okay, so these are the properties of a set. Abelian is not necessary in our just group, but if the group satisfy this type of property or commutative property, then it is called abelian group. Okay, for group you have to just clarify these three properties. First of all, binary operation means the set is closed under that binary operation. After seeing closeness, you have to see either the set is holds associative property or not. Then you have to see either the identity element exists in it or not. Then you have to see inverse of each element exists in it or not. So we see what is set. Now we see some examples of sets or infinite sets. A set can be finite or infinite. How we know a set is infinite or infinite? If a set is finite, then it has fixed number of elements, because for example, if we have 0, 1, 2, then it is a finite set. But if we have the elements 0, 1, 2, and then so on, so these are our infinite sets. So according to the set, if a set is finite, then our group is finite. If a set is infinite, then our group is infinite. So for with the help of infinite sets, we see infinite groups. And in the previous video, I clear that what is Z, set of integers, set of Q, rational numbers, set of real numbers, complex numbers, and these are all abelian groups. For abelian groups, for example, you see set of integers under addition. Here, addition is our binary operation. So set of you read it, set of Z under addition is abelian group. Set of rational number under addition is abelian group. Set of real numbers under addition is abelian group. How you conclude that these are our abelian groups? So let's take set of integers and try to show our statement is true or false. So you know, set of integers include all positive and negative element and 0. 0 plus minus 1 plus minus 2 and so on. So on mean plus minus 3 plus minus 4 plus minus 5 plus minus 6, all continue. Okay, so 0 plus minus 1 plus minus 2 and so on. So this abelian group, for the abelian group, first we have either our set. First of all, we know nothing about this set. We have just a set and it is set of integers, and just we know it is set of integers and it have such type of element 0 plus minus 1 plus minus 2 and so on, and now we know nothing about it. Let's try to prove the properties one by one. First of all, we see either it is closed. Closed mean under addition, mean plus is binary operation or not. For first of all, we see the operation which we applied on our set is binary or not. For binary, we see either it is closed or not. So for closeness, we see sum of two elements is again an integer, sum of two integers, and you know sum of two integers is again an integer. You add 1 plus 2, it is 3, and 3 is also belong to z. You add 2 plus 5, it is a 7, and 7 is also integer. So from here you clearly say that set of integers is closed under addition, and closeness property is also called binary operation. So these are the two different names of the same concept, binary operation and closeness. So don't be confused with it. So first of all, we see about its binary operation, either it is binary operation or not, and we clear that from this set it is our binary operation. Next we see associative property. Associative property means first of all, take three elements of integers and add them and see the result. And if we take three elements 0, 1 and 2, so 0 plus 1 plus 2, change the bracket, first of all add 1 plus 2 and then 0, then it is 3, and first of all add 1 plus 0, then add 2, then it is also 3, mean 3 is equal to 3. Our associative property hold in this case, so it is the right set of integers clearly again here, 0 plus minus 1 plus minus 2 and so on mean continue. Next, all elements of such type of elements. So first of all, we see either it is closed, then we see associative property hold in it or not. Now we see either it is closed, identity element exists in it or not. And you know what is identity element? Identity element is that is such type of element which we operate with all other elements of that set and our results remain unchanged. So 0 plus 1, 1, 0 plus 2, 2, 0 minus 1, minus 1, 0 minus 2, minus 2. So 0 is the such particular type of elements which hold this property, and so that's why 0 is our identity element. Here we see associative property, identity element. Now we move forward towards inverse. So what is inverse? Inverse of each element exists in a group. So inverse means when you add two elements and our results become 0. So plus 1 inverse, you know, is minus 1, and minus 1 includes in set of integers, because set of integers include all positive, all negative elements. So 1 plus 1 is equal to 0. So here 1 is the inverse of minus 1, and minus 1 is the inverse of plus 1. So plus 1 also include in that, minus 1 also include in that set. So that's why inverse is also exists. And you know, associative property also hold in integers, commutative property also hold in integers. Why commutative property hold in integers? Because sum of the two elements, two integers, and changing their position does not make an effect. So that's why integers is an abelian group. Similarly, try to satisfy all the properties of the group and try to solve these, and you will conclude the set of rational numbers is an abelian group, set of real numbers is an abelian group, set of complex number is an abelian group. And what is Z star? Here I write Q star. Q star means set of rational numbers, but star means without 0. Set of rational numbers, but 0 is not included in that set. And with respect to multiplication, is dot mean multiplication is an abelian group. Q mean involves 0. Rational numbers, just where we write simple Q means set of rational numbers with 0, and when we write Q star, then we mean set of rational number without 0. So R star mean is abelian group, and R real numbers, and you know real number is very important set which hold all the properties. So set of real numbers is also a group. So this is a billion group, but with respect to multiplication, but zero is not included in that. Let's suppose we include zero in that set. Then what happened? Then when we include zero in that set, then inverse of zero with respect to multiplication is not exist. And when inverse is not exist, then it does not become a group. So that's why we have to minus zero, and after minus 0 we remain the such type of set, then this is the group under multiplication. So keep in mind, you have to satisfy all the properties of set, and when we include 0 in that set and apply operation multiplication instead of addition, then our results change. And if we include 0, then inverse not exist, then it is not a set. But if we exclude 0 and see all the properties of a group in that set, then we conclude that it is group, and it is a billion group, because in real numbers or in rational numbers, multiplication associative property with respect to multiplication. First of all, for example, 2 multiplied by 3 is equal to 6, or 3 multiplied by 2 is equal to 6, means our answer remains unchanged. That's why rational number is in abelian group, real number, and this is complex numbers. And complex number is, it's our great test set, and on complex set of complex numbers we have to satisfy all the properties of a group. That's why complex number without 0 under a bill is a group, and it is a billion group. A group is not necessary to be an abelian group. In particular case, it is be an abelian group. Next, we see such type of example. You see here, I give all the examples of a group which are group as well as abelian groups. Otherwise, abelian property is not necessary for becoming a group. That's why in example 9, I give one example which is group, but not an abelian group. Set of matrices, in set of matrices, multiplication of two matrices mean you multiply if you have two matrices one at matrix A and other matrices B, and multiplication of matrices is not associative, because in matrices general AB is not equal to BA. So that's why our identity set of matrices is a group, but it is non-abelian group, because in abelian group you have to satisfy commutative property with the help of under our given binary operation. So here one example, it is very common question that that every teacher can be asked, or every student of group theory must to be know. Give two reasons why natural number is not a group. They say set of natural number is a group, but is not a group. But why? Reason, set of natural numbers have the elements starts from in previous lecture I cleared that set of what is set of natural number. Set of natural number is such type of collection which starts from 1, 2, 3, and then so on, continue. So this is our set of natural numbers, and set of natural number is not a group. Why? Because and under addition, and binary operation is addition, and in addition here associative property hold, no problem. But you see in under addition our identity is 0, but 0 is not included in that set. That's why our identity miss here. So if identity miss, then our inverse automatically does not exist in here, because identity does not and identity and inverse dependent from each other. So that's why it is not a group. So if someone ask you why natural number is not a group, then you have a clear idea about that. inverse of 0 does not belong to a set of nature number. That's why inverse does not exist, and identity also does not exist. So we have one other question. Determine G is a group of the given set. Cyclic group. First of all, G is a group of the given set. This is the most asking exam question. So try to answer this question by yourself and then tell me. Cyclic group. What is cyclic group? Let G plus is a group and let G is said to be cyclic if 0 does not equal to A belongs to G such that N A and N belongs to Z. For example, in this cyclic group, one element is the generator, can generate all these groups. So the element which generate all other elements of that group is called generator. And for the generator, this is our sample. This is our sample for generator. All the elements are generated by A. For example, A square, A cube. For example, you have a such type of element A, then A square, then A cube, and so on, A4, A4, A5, and so on. So you see here A square, A cube. So all these elements can be generated with the help of A. Here we 1 multiply by A, then A multiply by A, then A square multiply by A. All these elements can be generated with the help of A. So that's why A is our generator. A can be vary from group to group and can be vary from group to group. So here is the generator. If G dot is a group and G is cyclic, if here we see G dot means if we have a set and it is a group and group with respect to what? With respect to multiplication. Here our binary operation is multiplication. Group under multiplication, then G is cyclic if 1 not equal to A such that, and here we have cyclic group have two definitions. When it has binary operation under addition and when it has binary operation under multiplication. When we have binary operation under addition, then our cyclic group become in this way N A, and for all N belongs to C. When we have a group and it has binary operation under addition, then we have the power of A. So for example, 1A square A cube, it is the group and it is group under multiplication. That's why here A is the generator. If G is finite, then N belongs to G and N is equal to 1. For example, here we see one example of a cyclic group and you see set of integers Z plus is a cyclic group, and you know what is Z, and Z have the element 0 plus minus 1, 1 plus minus 2 and so on, and you know 0, all these elements can be generated with the help of 1. 1 is the multiply 1 multiplied by 1, 1 multiplied by 2 is equal to 2, 1 multiplied by 3 is equal to 3, and so on. So that's why here 1 is the generator of the set of integers. Then you have you see here Z is infinite set. So set number of generators also depends our set is finite or infinite. So first of all, you see our set is finite or infinite. Then after that you determine our generators of that set. So if mean every element is multiple of 1, so 2Z, here 2Z, 0 plus minus 2 plus minus 4 and so on, and here this set can be generated with the help of 2. So here 2 is the element, is the generator of that set, cyclic group. So now we look forward another important definition of a group theory, and which is the order of the group. Here we see two different terms, order of the group and order of an element. What is the order of a group? The order of a group is the number of elements in it, and we write the order of G. Means order of the group is the number of elements in a set. For example, if you have one set and it has, for example, if you have one set and it is A, B, C, and D. How many elements this set contain? You see clearly it has 4 elements, and so we name this set A. So order of A is equal to 4, mean number of the elements in a set is the order of the set. Or if a set has infinite order, for example, if infinite elements 1, 2, 3, and so on, then it is infinite order. Its order is not defined and it is infinite. Okay, so order of an element, here order of an element is totally different term of order of the group. Let G be a finite group of order and an element X belongs to G is said to be order of M if X raised to power M. For example, you have one element and you add other identity element, one other element in it, and you got identity element. How many times you add other element in element A, then this number is the order of that element. We see the example of order of element and try to clear next. So here is one another important term, and this is the subgroup. You see every set has a subset. Similarly, every group has a group, and every group has a subset of if group is defined on a set. So in the same way, subgroup is also defined on a set, but subset of our original set. First we take some subset of our original set, then apply the binary operation on that set. If it contain all the properties of satisfy all the properties of the set, then it is the subgroup. And for example, Z, and if we take some elements and subset of Z, 2, 0, 2, 4, 6, and so on, 2Z is the subset of Z, and 2Z also satisfy all the properties of a group. That's why 2Z is also a group, but 2Z is the subgroup of Z. Okay, similarly, set of integers belongs to set of rational numbers. Q subset is rational numbers, so that's why set of integers is the subgroup of set of rational numbers. Similarly, set of integers is subgroup of real numbers. Set of integers under multiplication is not subgroup of under this, and this is not is subgroup of under this. So here we see counter examples and other examples to clarify our definitions. Here we have some important remarks, and that remarks are very important in our learning point of view. Every group of an infinite group is infinite. For example, you have infinite group, then it has must have infinite subgroup, or every subgroup of a cyclic group is cyclic. For example, if you have a group and it is cyclic, then it must be a cyclic subgroup. Every group of an abelian group is abelian. Abelian, you know what is abelian. Abelian is such type of group which satisfy commutative property with respect to that binary operation. If commutative property with respect to that binary operation, which is defined on our set, hold, then it is abelian. And abelian group have subgroup also abelian. So here we discuss some important concept and theorem or proposition about this. Every cyclic group is abelian. Now you see what we learn. We first of all we learn what is group, then what we learn which property we can add and make it abelian group. And from abelian group we study cyclic group, and here we discuss about relationship between cyclic and abelian group. And every cyclic group is abelian group. The group which is cyclic, then it must be abelian group. But a group is abelian, then it does not necessary to be a cyclic. So make a clear idea from statement, and do not reverse it when other or when the theorem asks us. So every cyclic group is abelian group. So let's prove this. How we say every cyclic group is abelian group? We have to justify our statements, And from this proof we clearly see that every cyclic group is abelian group. Let G dot be a cyclic group and there exists A belongs to G such that G is equal to or A. For example, G is a set which is generated from A, and you know the set which is generated by some elements, then it has A is the generator of that set, and this set is called cyclic set. So cyclic group. So XY belongs to G. Let we have two elements and two elements of G, and X is equal to A raised to power M, and MK belongs to Z, and when we apply binary operation and add these, and this is also over. So from this you see that every cyclic group is abelian group. So from here we discuss about cyclic group and some important theorem about cyclic groups, and we see every cyclic group is abelian group. And here we see some important remarks, and our remark is that every abelian group is not cyclic, because you see every cyclic group is abelian, but every abelian group is not cyclic. And to prove some facts, we can give, or we have to give a clear counter example. You see Z plus is a group, and Z is one is the generator of the set of integers, so Z is a cyclic group. But Q plus is an abelian group, commutative law hold in it, and Q plus is not cyclic group. So abelian for us, abelian group needs not be a cyclic, but every cyclic group is abelian group. Let G be a group and A belongs to G, then generator of A over cyclic group is a subset of G is a cyclic group. This is the proposition, and this proposition say that every cyclic group has abelian cyclic subgroup. Means subgroup of a cyclic group is cyclic. Okay, so see one example, and here we have Q set of rational number 1 over 2, 1 over 3, 2 over 2 means 1, 3 over 2, and so on. And here 1 over 2 is belongs to Q, and 1 over 2 is the generator of all these elements. If it is the generator of all these elements, then it is a cyclic group, and this is the subset of Q. So that's why subgroup of a cyclic group is cyclic. So finite cyclic group, here you know we have two main definitions, finite and infinite. First of all, we study about infinite. We see what are the abelian infinite groups and non-abelian infinite groups. Now we look more forward to finite cyclic group, and in Zn are set under addition modulo n. What is modulo n? This is the such type of the set 0, 1, 2, and 3, so on, and -1. So this modulo can be defined as this: if you add these two elements, and if our answer less than n, then you have to write the sum as it is. But if our answer greater than n, then you have to write remainder of. For example, now let's define, I define the modulo with the help of example, so you can clearly understand about that. So you have two definitions, two set, one set 0, 1, 2, and it is a set under modulo 3. Okay, here n is 3. So when you add these two elements, for example 1 plus 2, 1 plus 2 is equal to 3, and you know n is equal to 3. So here we cannot write here 3 as it is, because we just divide 3 by 2, and 2 ones are 2, and we have remainder 1. So we write here remainder here, so 1 is our resulting answer. But if our answer less than n, mean if we add 1 plus 0 and 1, so less than 3, so if we write 1 as it is, and do not need to divide it and anything else. So what we learn from that? We learn what is finite cyclic group under modulo n. Here see some important point where R is a remainder. When a plus b is divided by n for n belongs to n, then this is a cyclic group generated by t and is of order n. For example, you have 0, a group of order 1 is 0, z2 is modulo 2, and here n is 2. Z3 0 1 2 3 mean it has 3 elements and starts from 0 and from 2 we complete 3. So n is 3 and here n is 4 and z4 and here n is 5. So z2, z3, z4, z5 and what is the order of that set? The order of set is the number of elements in that set. So in z2 order of this set is 2. In z3 order of this set is 3. In Z4 order of this set is 4. So order of Zn is equal to n. In order of each element Z2, Z3, Z4. So you have to find order. First of all, you make cayley table. This is the cayley table, and first of all, that's why I want to give lecture about cayley table, because with the help of cayley table we define whether a set is a group or not, whether a set is abelian or not, whether a set is cyclic or not, and all other basic terms and definitions of a group. So that's why cayley table is most important. So we study now about cayley table, then we move to next. So for the cayley table, first of all we study about cayley table. What is cayley table? So cayley table is, Cayley is the name of the mathematician, and Arthur Cayley was a prolific mathematician who worked mostly in algebra. His contribution towards algebra is never forgettable. So he handled calculations and guided by a deep intuitive understanding of mathematical theories and their interconnections. His ability to keep abreast of current work with seeing the wider view enabled him to perceive important trends and to make valuable suggestions for further investigations. So here we see, that's why I think in previous 1 or 2 minutes my screen is not sharing properly. That's why I repeat the sentence again. Arthur Cayley. Arthur Cayley is a prolific mathematician who worked mostly in algebra. He handled calculations and guided by a deep intuitive understanding of mathematician to perceive important trends and to make valuable suggestions for investigation. So we discuss about cayley table and importance of cayley table. Why we study cayley table and how it is important in our next concepts. Many properties of a group, such as whether or not it is a abelian group, which elements are inverses of which elements, and the size and contents of the group center. So all these things can be easily concluded with the help of cayley table and can be discovered from its cayley table. We can be discovered all these things from its cayley table. Here see what is cayley table. If G is a finite group with the operation star, star means binary operation. The cayley table of G is a table with rows and columns labeled by the elements of the group. The entry in the row labeled by and the column labeled by this group is G star H. For example, you have to write all these elements in row and column and multiply these row and column elements and write it in a table. So let's see with the help of example this definition and try to understand how we multiply and how we write the elements in a cayley table. So you see here we have a group and it is Z5. Z5, you know, it is a set of integers under modulo 5 and it has 0 to 4 elements. So for first step is to write the elements of these set of a given set in rows and columns, and then multiply our binary operation addition. So add these elements. So for example, 0 plus 0 is equal to 0, 0 plus 1 is equal to 1, 0 plus 2 is equal to 2, 0 plus 3 is equal to 3, 0 plus 4 is equal to 4. Similarly, 1 plus 0, 1, 1 plus 2, 2, 1 plus 2, 3, and all. Write all these elements, and we reach 4, and 4 plus 0, 4, 4 plus 1, 5. Why I write it 0 instead of 5? Because in modulo modulo 5, you have to write 4 elements, and if our our answer is a 5 or greater than 5, then we have to write its remainder. And when you divide 5 by 5 and its remainder is 0, that's why I write here 0. So why I write here 1? For example, 4 plus 2, 6, and the remainder of 6 after dividing 5 is 1. That's why I write it here. So similarly, 2 and 3 are also remainder of 7 and 8. So this is cayley table. What are the features of cayley table? First, you know, every definition and concept have great importance in group theory. So we have a clear purpose why we study cayley table. Cayley table, every group, row and column of the table should contain such element exactly once. Let's see previous. Every row contain all the elements exactly once. For example, if you have these rows 0, 1, 2, 3, 4, so 0 to 4, none of the element repeat. 2 exist here, once 3 here, once 4 once. So that's why all the elements of the row and columns appears exactly once. So this is the one of the most important feature of cayley table. The identity element of the group should not only appear in every row and column exactly once, but it should be also distributed symmetrically. For example, the identity element of the group should not appear only in every row and column, but it should also be distributed symmetrically in diagonal. So see this, you see here what is identity? This is symmetrically diagonal. Diagonal, you know, here identity element. 0 is the identity element, or you see, sorry, I pointed at one. This is our identity element, and identity is distributed diagonally, because you know in diagonal can be this or this. For example, this is a matrix, and this is our diagonal, and this is one diagonal. So 0, 0, 0, 0. This sequence is the magic of cayley table. So that's why they say that all the elements of the cayley table distribute identity elements. Okay, identity elements distributed symmetrically. Okay, first we see every row and column of the table should contain each element exactly once. Okay, next we see the symmetricity of identity element. Now we move forward other properties. Otherwise, not or more elements in table do not have an inverse. Okay, because if this is important for our inverse. Features of cayley table. There should not be any entries in the table that is not a row or column label. Okay, all the entries repeat in a cayley table are very familiar elements, or these are the elements which we write in our row and column, and none other unfamiliar element cannot be written here. So otherwise the operation is not closed. So for closeness, you have to see either all the elements of row and columns are appears in that table, or none of the element is outside from our rows and columns happens here. So this for this we have to clarify about closeness. There should be one row in each in which the column labels appear in order. This indicates the presence of an identity element. The column of these elements should reflect the row labels, otherwise there is no identity. If the Cayley table is symmetric along its diagonal, then the group is abelian group. If the Cayley table is symmetric, then it is abelian group, and if Cayley table is not symmetric, its diagonal, then it is the non-abelian group. So from these features, you made clear idea about the importance and how we use Cayley table in our groups to determine whether it is a abelian group, whether it is closed, whether it has inverse or not, and all other features. So these are very important. So now we move forward our next definition, which we passed, because here importance of Cayley table is very important, because in our next lecture we used Cayley table. That's why I first of all make a clear concept about Cayley table. So after reading about Cayley table, we make a Cayley table of Z2, Z3 and Z4, 5 here. This is the Cayley table of Z2. Z2 have two elements, 0 and 1 and 0 and 1. And you know, first for making Cayley table, first of all we write 0 and 1 in row, then 0 and 1 in that row, then according to our operation we add these. 0 plus 0 is equal to 0, 0 plus 1 is equal to 1, 1 plus 0 is equal to 1, and 1 plus 1 is equal to 0. Why we write here 0? Because you know in modulo 2 we cannot write 0, or we must write its remainder. So 2 has remainder 0 after dividing by 2. So that's why you see it is symmetrically distributed, and it is Z2 is a group and it is a abelian group. Okay, so Z2 can be generated with the help of a 1. Okay, here what is 1 bar? 1 bar is the show for modulus property. So this is the Z5 Cayley table, and from this you make a clear idea about its group. So this similarly order of 2 is equal to 5, order of 3 is equal to 3, and order of 4. Why how you estimate about order of each element? For example, you have 2, and for here you I tell you about how we calculate order of each element, because you know, first of all, after reading the definition of a group, cyclic group and abelian group and some properties of the group, we see two definition: order of the group and order of the element. And order of the group is simple, the number of elements in the group is the order of the group, but order of an element is a little bit difficult, more difficult than other. So 1, let's see 2. What is the in order of 2? Order of each element, we can determine each order of each element. Each means 0, 1, 2, 3 can be element can be 0, 1, 2, 3. So now what first of all we see order of 2. You see here identity where come row, then this it goes to there, then this element is our order of that element. So 2 have the 2 is the identity in that row. So 4 2 has the inverse, and it is 2 has inverse and its inverse is 4. Similarly 3 comes here, and so inverse of 3 is 3. So 4 identity comes here, so inverse of 1 is 6. So from this you make a clear idea about the order of the each element in a group, and it is very important topic. Similarly order of 2, 5, 3, 5, 4, 5 and so on. Z4 0, 1, 2, 3 and this MCQs type question. two sets are equal, A, B, C and B, C, A. Two elements are equal when A is equal to B. A subset of B or B subset A. Or this is the, first of all, we have two sets and we set these two sets equal when we have same elements in a set. Mean A is the subset of B and B is the subset of A. So from this we conclude that A is the subset of B. So now we move forward next, and here is the one example. Find the order of 16 and 48 and -6 and 144 in Z36. And you know, in Z36 how many elements we have? Z36 we have exactly n minus 1. Zn we have exactly n minus 1 elements. So in Z36 we have Z35, 0 to 35 elements, and its generator. This is the definition of modulus, and we have to find the order of 16, and divisor of 16 are 1, 2, 4, 8, 6. So 8 and 16 are does not divide 36, then 16 has greatest common divisor 4. So this is the order of this. From this is very easy method to find order of C group. Now let's see one important remarks, and this is the order of about order. Order of A belongs to Zn. For example, order of each element or order of an element A which belongs to Zn. What is Zn? Set of integers under modulo n is A, and its formula is, for example, for calculating all the elements of set and making cayley table is very difficult task, and so this is our formula. With the help of this formula we can write order of the group easily. So order of A is equal to n over GCD over AN. What is GCD? GCD is greatest common divisor. Greatest common divisor n and AN. For example, you have a set Z5, or you have to find the order of 3. So in Z5 write 5 here, and GCD of 3 and 5. 3 and 5, and you know GCD of 3 and 5 is 1, because nothing common in 3 and 5. That's why 5 over 1 is equal to 5. That's why in Z5 order of 3 is equal to 5. So from this formula we can make we can find order of each element in a group of Zn easily, and with GCD you just have to clear that what is GCD and put all these values in this formula, and you will get your desired answer. So here is some exercise, and you have to done it by yourself. Find the order of this in Z28. You know, in Z28 set contain n minus 1 element. So 28 minus 1 mean 27. So it has 27 counting numbers, 0 to 27. So now we have to find the order of 1. So 1 mean according to formula n over GCD over our element whose order we have to find, and our total n. So 28 over GCD of 1 and 28, and GCD of 1 or 28 is 28 because nothing is common in 1 and 28. Certainly 1. So 28 over 1 is equal to 28. So order of 1 is 28. Now we have to find the order of 5, and here 28 and 5 over 28. So here nothing is common between 5 and 28. So GCD of 5 and 28 is 1, and here on upper side we have 28, and 28 by 1 is equal to 28. So order of 5 is 28. And similarly we know order of 14, and 14 minus 14 is equal to plus 14, and order of 14 is 28 over 14 over 28, and you know 14 and 27 is the common divisor and greatest common divisor. So 28 by 7, and when we divide 28 by 7 we have 4. So order of 14 or minus 14 is 4. Okay, so from this formula we easily make the conclusions about this and make know about order of each element. So what we learn today, so here we see what is group, then after group we see what is order of the group, what is finite group, infinite group, cyclic groups, and some important theorems or propositions about cyclic or infinite cyclic groups and order subgroup. Or now we see some examples of a finite group and some example of how to and formula about how to find the order of each element in a group. So this is one another important example, and Z12, and you have to write all the orders and generators of Z12, and this is the solution, and you try it by yourself, and hopefully you will get the right answer. So after that, see these three important remarks. If n is prime number, then every element of ZP is a generator of ZP. For example, if you have Z3, Z5, Z7, mean here prime numbers. So ZP and P is prime number. So all the elements are generators. Here, as you see in Z3, 3 is prime. So in Z3, all the elements are the generators of that set. Okay, every group of order P is cyclic. The number of generators in Zn are all these elements of Zn which are relatively prime to n. Relatively prime to n. So these are three important remarks about what we learned and conclusions of today's lecture.